Okay, we left off with contraction. So now that the active sites on the thin filaments are available, actually, did I just say that wrong? Let me backtrack. Yes, the thin filaments. So the active sites on the actin are available. Then we move into the phase of contraction. And again, I would watch these animations because they really do a better job than these two-dimensional pictures. But again, all of them are good. This is good at breaking it down into steps. We know that ATP is needed for muscle contraction, and so the ATP is broken down into ADP and a phosphate group, and that is the activation and cocking of the myosin head. That ATP gets it going, using that ATP, I should say. And then once that occurs, then the myosin actually attaches to the actin with a structure called a cross bridge. So the ATP breaking apart is what activates the head, kind of cocking it, getting it ready into extended position, and then the head binds to actin active site, forming a cross bridge, and that is an important structure to know, that cross bridge. Okay, once the head releases the ADP and the phosphate group, it pulls the thin filament past the thick filament. This is called the power stroke. Again, the animation is going to do this much better than these pictures are doing. And then upon binding more ATP, the myosin releases the actin and the process is repeated. So each head can perform 5 power strokes per second, and each stroke utilizes 1 molecule of ATP. So it's, I always think of it kind of like pulling a rope, hand over hand. It is creeping on over, moving along that actin. Again, absolutely watch all these animations and other animations. All the animations you can find will help this become much more understandable. Okay, so once all that is done, the nerve stimulation is going to stop. I shouldn't say that. The contraction doesn't have to be done for the nerve stimulation to stop, but when the nerve stimulation stops, the acetylcholine release also stops, and the enzyme then breaks down the acetylcholine and the fragments, and they're reabsorbed into the synaptic knob, or back up into the nerve fiber. And so the muscle cell that was stimulated by the acetylcholine, that also stops because the acetylcholine is no longer there. I like this part of the process because it reminds me that anytime you have a stimulus that keeps going, the process is going to keep going. So this helps me understand that once the acetylcholine is broken down and it's no longer stimulating the muscle fiber, then the contraction can stop. Then also during relaxation, the calcium is pumped back into the sarcoplasmic reticulum by active transport. Again, that's low concentration to high concentration, requires ATP, and then the calcium is going to stay in storage in the SR. So ATP is needed for muscle relaxation as well as contraction, which is something that's really weird to think about. But if you understand active transport, then it makes sense. We need ATP for that process to put the calcium back into the SR. And this says the exact same thing, just in a few more words. And so the tropomyosin is going to move back, reblocks the active sites, and the muscle fiber ceases to produce or maintain tension. So the muscle fiber is going to return to its resting length. Again, you need to be in presentation mode or presenter mode to be able to watch those, or you can just Google them separately on YouTube. So rigor mortis is the condition where the hardening of muscles and stiffening of the body and begins 3 to 4 hours after death. So what happens is the sarcoplasmic reticulum starts to deteriorate and releases calcium ions. And of course the sarcolemma is also deteriorating, and so calcium ions are allowed in. And then that activates the myosin actin cross bridge, and the muscle contracts but cannot relax. We know that the relaxation requires ATP, and after death, the body is not producing any more ATP, so the muscles remain contracted until the myofilaments begin to decay. It peaks about 12 hours after death and then diminishes over the next 48 to 60 hours.